So today we're going to continue the lecture on multi-core and parallel programming. Um, we talked about how to change a serial program to a parallel program, or especially when you in the design process, how do you do the decomposition of tasks and data. Today we're going to introduce correctness concepts. Some of you have learned this from other courses, for example, operating systems. But I just want to give you a quick review of these concepts. And later we're going to introduce tools to understand the performance of these parallel programs. And these concepts will be very helpful. So we're going to talk about the critical region, mutual exclusion, and synchronization. Also, we're going to talk a little bit about this race condition. Race conditions happens a lot in concurrent programs, and they oftentimes the cause of the errors. The race condition occurs because the programmers assume a particular order of execution, but when the program actually is executed on the processor, there's no guarantee that this order will happen because no proper synchronization mechanisms are applied in designing a program. A data race refers to storage conflict situation. So you have shared data among multiple threads. Data race will happen when two or more threads simultaneously access the same memory location, while at least one thread is updating that location. So if all the threads only read from that location, things are fine. But if there's one thread that's going to write to that location, if you do not do proper synchronization, the other threads may not see the consistent data. There were two possible conflicts, read/write conflicts, which refers to that one thread or multiple threads reading while one or more threads are trying to write. Similarly, write/read conflicts refers to that one or more threads are writing to the same location. Critical region is a part of your code where access is supposed to be controlled. And this critical region must be protected to ensure data integrity when multiple threads tries to share or to access the shared resources or shared data. Critical region, by concept, that refers to the fact that you only allow up to one thread to access that region. If the region is a piece of code, remember all the threads share the code space. So they essentially execute the same set of instructions, same stream of instructions. Critical region of a code space refers to part of the code or a sequence of instructions are only allowed to be entered, to be executed by one thread at a time. Mutual exclusion refers to the program logic used to ensure single thread to access a critical region. So with mutual exclusion, with the proper APIs, that you can ensure that even this program is executed in a multi-threaded way, only one of the threads can enter this part of the code at a time. Synchronization is similar in the sense that it's the process of implementing mutual exclusion to coordinate access. So you can use synchronization functions or primitives to ensure that thread A is preceding thread B, and thread B is preceding thread C. So you can build such order of access so that the thread can enter the critical region one by one, or in some other cases they access a shared variable in a predefined order. Barrier synchronization is one interesting method of doing synchronization. In this case, all the threads must finish a portion of the code before proceeding to the next section of code. When you have concurrently executed threads, even though they are executing the same set of instructions, the sequence of these execution may be different. That means the order of these threads finishing the code will be unpredictable. This barrier synchronization is to say that no matter how these threads are executed, no matter which one is preceding which other one, all of them have to be completed at some point before the program, before any of them can proceed to the next stage. It is usually done to ensure that all updates to the section of the code prior to the barrier before the threads begin execution that passed the barrier. Deadlock is when the threads wait for a condition that will never occur. The most common cause of deadlock is because the competition among threads for system resources which are held by other threads. There are 4 necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. So it's easy to understand. For example, the traffic jam. The traffic from all 4 directions are trying to proceed. So they enter the intersection, they block the other one. As a result, none of them could proceed. So that's the deadlock. Livelock is similar to deadlock, but the major difference is that even though the threads may be executing some instructions, but the end effect is that even though these threads are still concurrently executing, they cannot move beyond a certain point. The threads are trying to overcome an obstacle presented by another thread that is doing the same thing. So it's kind of doing this. There's one picture here. Robin Hood and the Little John, they just try to fight each other. None of them will give up. So they're still doing something, but the end effect is that they're not going anywhere. Next, I want to introduce some performance concepts in terms of the speedup, computing speedup, efficiency, granularity, and load balance. The definition of the speedup is very simple, intuitive. The speedup is essentially the serial execution time divided by the parallel execution time. Because normally the parallel execution time will be shorter, so the speedup you expect to be a number greater than 1. According to this Amdahl's law, we can calculate the speedup in a different way if we know the fraction of the program that is to be optimized by executing the task in parallel. So what we're seeing here, this formula, we have this task. Let's say the original execution time is 1. S here is the fraction of time that cannot be parallelized. So this has to be executed in series. Whereas the other part of the workload, which is 1 minus S, this fraction of the code, the whole task, can be executed in parallel if we have n processors. So for example, if I have 20% of the work that cannot be redesigned in parallel in multi-threaded threads or be executed in multiple processors, this is the 20%. So we have 80% of the workload. Let's say if we have 8 processors to carry out these tasks, so this part will become 80% divided by 8, so that's 10%. The last term here, this is the overhead. If you rewrite your program, a serial program into parallel program, you have to introduce oftentimes these synchronization primitives. You have to do locks, you have to do PV operations to synchronize these threads. So those operations are considered overhead. So this could be 1% or 2% depending on your design. So what you end up having is this is the 20% that you cannot speed up, and this is the portion of work you can speed up. So 80% now becomes 10%. So this 20, 10, this could be, let's say, 1%. So overall, time you need to finish up this parallel design will be 31%. So you do 1 over this 31%, and that's 3 point some speed up. We have example that shows you how to compute the speed up. Let's say we are doing this work. We're painting a picket fence, which requires 30 minutes of preparation, and that's a serial task you cannot optimize. And you need 1 minute to paint a single picket, and you need another 30 minutes to clean up, which is again a serial task you cannot optimize. Now we can have these ways of executing or finish up this task. We use number of painters as the n, so that's how much parallelism you can exploit. Let's say that's how many processors or servers you can have. And if we have only 1 painter, if we want to paint 300 pickets, so that will be 30 for the preparation plus 300 for doing all the work plus 30 to clean up. So the total time is 360. And let's use that as the baseline. Okay, let's say the baseline. If you have only 1 painter, you only you will need 360 unit time to finish the work. If you increase the number of painters, now this 30 and this 30 cannot be optimized, but this 300 is now reduced to 150 because n is 2. So you divide 300 by 2. So the time you need becomes 210 time units. Compared to this 360, you have 1.7 times speed up. So you can do this way continuously. Let's say if you have 100 painters, this 300 becomes a 3. So now the execution time is 63 units. This is the serial time and this is the parallel time. So you divide this 360 by 63, so the speed up is 5.7 times. In theory, if you have infinite number of painters, this time it's going to be 0. So the ideal case, or the ideal speed up, is this 6 times speedup. Parallel efficiency is a measure of how efficiently processor resources are used during parallel computation. The way to calculate is to use the speedup number divided by the number of threads and times 100%. This is essentially to measure, given n processors, how busy they are in this whole process. If we use this formula in the case of one painters, because this painter has to do all the work by himself or herself, so the efficiency is 100%. Because the speedup is 1, the number of threads is 1, so you get 100%. If you increase the number of painters to 2, the speedup, as we calculated, is 1.7. You divide it by 2, because there were 2 painters. You times this 100%. So that gives you 85%. That means for these 2 painters, during this 210 time units, 85% of time their time are busy, and another 15% of time they don't actually do much of the work because of the serial execution part of the workload. Now, what's very interesting is that we know when we increase the number of painters, the speedup keeps increasing. However, on the other hand, the efficiency keeps decreasing because the speedup has an upper limit, right? In our case, it's determined by the portion of the serial task, the serial portion of the whole task. In our case, that's up to 6 times. Where you keep increasing the number of painters, the efficiency keeps dropping because the denominator, this n, is increasing. That means as you have more painters, even though the overall execution time is reduced, but these workers are not that busy all the time. Granularity is an approximation of the ratio of computation to synchronization. So imagine that you have 100 instructions to execute. When you rewrite this program in parallel, you want to take some portion of the code that try to let them execute, let them finish with multiple servers, multiple threads. You can chunk off these instructions out of this 101, and you can try to assign these individual instructions to individual processors or cores. So this is what we call fine-grained. In contrast, if you just take this whole application and give the whole thing to one processor and a copy of the 100 instruction to another processor, then that's the coarse grain. So it's determined by how frequently you want to do this synchronization because you are running this program on different threads or different processors. If this synchronization happens very often, every a couple of instructions, compared to a different implementation where the synchronization happens in 1,000 instructions. So that's first case is a fine grain, and later case is a coarse grain. Of course, we don't have a precise threshold. How low is the fine grain and how high is the coarse grain? It's just relatively speaking. Load balance, intuitively, you know that once you have multiple workers, multiple cores, you want to balance the workload. You don't want to overload one processor while let the other processor idle. the more balanced the work, the higher efficiency you have. So the goal is to distribute the work across multiple threads so that they all perform roughly the same amount of work. If you think differently, if all the work to all the threads are even, they will finish at the same time. If one single thread takes double of the work, that means this particular thread has to take extra time to finish compared to all the rest of the threads which finish ahead of time. So the end effect is that your execution time is delayed by this prolonged thread execution. So most effective distribution is such that threads perform equal amount of work. Threads that finish first sits idle, and thread finish work close to the same time. And in this picture, obviously this is not balanced workload. And the end result is that you will not clean up the banquet tables until the very first one finish all his share. And he's not happy about it. So in summary, we talked about in this set of slides concept of threads and the benefits of doing multi-threading. Also the risks of using threads in a design. For example, data races, deadlocks, and also increased code complexity and portability issues. One important thing you want to be aware of is all the threads within the process share code and data segment. And that's why the context switch overhead among threads is much smaller compared to the context switch among processes. Concurrent threads can execute on a single processor, where parallelism requires multiple processors. We talked about turnaround time, and we compared that to throughput. We discussed how we do decomposition in our design. We talked about functional decomposition, data decomposition. We described race conditions and critical region and how we can design threads so that critical region can be enforced. Basically, we want to ensure mutual exclusion of threads, and using synchronization primitives, we can guarantee that only one thread going to that critical region. We compared Deadlock with Livelock, and we give you an example of calculating the speedup. Amdahl's law is something you want to remember so that you can use it to calculate the theoretical speedup of your design. Also, we talk about parallel efficiency, granularity of the parallelization, and how to achieve load balancing.